Hello everyone, and welcome to another video tutorial in this series of tutorials for Item Toolkit, the world-leading software tool for all your reliability, availability, maintainability, and safety analysis. In this tutorial, I will walk you through on how to use the Item Toolkit Reliability Block Diagram Module, or RBD for short. Earlier in this series of tutorials for Item Toolkit, we looked at the reliability prediction modules to obtain the overall failure rates for our system, and we also looked at the FMICA module, where we carried out a root cause analysis based on the failure modes for our components and end effects for our system. In both the reliability prediction and FMICA modules, all components in our systems are assumed to be in series only, and there are no provisions to study any other configuration for our system, such as series and parallel, or any other configuration. The Reliability Block Diagram module in Item Toolkit is primarily used for availability studies whereby our components and/or our functions can be arranged in series or parallel, or any other configuration to obtain the availability of our system for a specific period of time, or what we call the lifetime for our analysis. As the RBD module is based on probabilities, it is imperative that we set the correct lifetime for our analysis, as the chances of failures or probabilities of our component or function failures would be much higher when studied over longer periods of time. As we have learned in earlier tutorials, we can easily convert our already built prediction or our FMICA systems to an RBD module. But let's first see how we would start building a new RBD. Let's open a new project and add a new RBD module to our project. As we have seen before, a new RBD system gets added to our project, and to work on this system, we would left mouse click on the bottom left side window. We see the project toolbar disappearing and the system toolbar for the RBD module, although not active yet, appears on the top right of our toolbar. Let's first look at our system parameters and the default values for all the system parameters. We do this by selecting the top node of the system window with the dialog View tab selected. Here we see various options for our analysis, and the main parameter being the lifetime, as I mentioned before. Let's set this to 1 year, which converted to hours is 8,760 hours. We can explore the other parameters as and when we need to, but for the purpose of this exercise, let's leave out other options as default. To construct an RBD, we would need to use the diagram view, and for this, we need to switch over to the diagram tab. And as soon as we do this, we see the RBD toolbar becomes activated. Here, we see a blank canvas where we can start to construct the configuration of our components and functions. Let's first take a look at our canvas size and settings. As we can see, we are able to scroll to the right as well as down. To check the current measurements for our canvas, we can go to the menu option settings, diagram measurements, and size. Here we can see that our canvas is set to 10 meters by 10 meters, which is more than enough for any system, small or large. Let's now see the settings for our page size and orientation when it comes to printing out our RBD diagram or exporting our diagram to a Word document. To do this, we go to the File menu option, Page Setup, and then Diagram Page Setup. Here we can see that by default our diagram page setup is set to A4 Portrait. Let's cancel this and show you the same setting in a different way. Here on the canvas, we can see a toolbar on the bottom of our screen, and one of the options is Toggle Page Bounds. Let's click this option to see a border appear on our canvas for the page boundaries. To further see these boundaries for the page setting A4 Portrait, we can zoom out of our canvas via a right mouse click option called Zoom. Let's set this zoom to be 50%. Now we can see all of our page boundaries for the current page size and orientation. Let's now go back to the Age Setup option and change our page size and orientation. Let's change the orientation to landscape and check the canvas. As we can see now, the canvas page boundaries have changed to A4 landscape. Let's now change the page size to A3 and see the page boundaries on our canvas. As we can see now, the page size is in A3 landscape, and we can scroll down or across to see these page boundaries for the entirety of our canvas. This is a very useful feature to help construct your RBD diagram to suit your requirements and making sure you are aware of any block falling off the page for the selected page size and orientation. Let's now put this back to A4 landscape. Turn the page boundaries off, put the zoom back to 100%, and start constructing our reliability block diagram. To construct a logical configuration of our block diagram based on our design, we would first need to introduce a starting node for our analysis. We do this by selecting the node from our toolbar and left-clicking anywhere on the canvas to create or insert this node. Now we can start adding blocks by first selecting this from the toolbar menu and then left-mouse clicking on the canvas to create these blocks. Let's arrange them in the configuration we need, and maybe a single block is series followed by 3 blocks in parallel followed by 2 blocks in parallel. As we can see, these blocks are given a new name based on the default settings and number sequencing. If we were to transfer from a reliability prediction or FAMICA module to RBD, then all the block names and descriptions would be automatically transferred along with the failure rates. In order to have control of the voting for our blocks in parallel, whether we need to specify a 1 out of 2 or a 1 out of 3 or a 2 out of 3 configuration, we would need a node after any blocks arranged in parallel. So, let's introduce a node for these blocks that we intend to set this type of M out of N or K out of N scenarios. Now we can also introduce an N node for our analysis and then start connecting these nodes and blocks based on our design. To do this, we would select our preferred type of connection, whether a straight line or right-angled lines with arrows, etc. It is entirely up to the user. Let's select the right angles connections with an arrow indicating the direction of the flow. Now we can start to connect our nodes and blocks by simply left mouse, click 1 on the output node of the node or block and the input node of the node or the block. We do not need to click and hold to drag. We simply do a 1 click and move the mouse followed by another click. So now that we have the desired configuration for our RBD analysis, we can arrange these blocks into a more presentable position by left mouse clicking on a block or a node, holding the mouse click down and dragging the item across the canvas to a desired position. To make it more convenient for the user, Item Toolkit RBD module has an option to do this arrangement automatically via this button on the diagram toolbar labeled Auto Arrange. Once we click this button, we can see that the blocks, nodes, and connections are all conveniently arranged to make our diagram much more presentable. Furthermore, the distances between each of the items can be configured in the menu option layout, Auto Arrange Parameters. By default, these settings are set to 1, so let's change this to be 5 and 5 to see what effect this has on our diagram. As we can see, now we have more distance between each item, which may be to the user's preference, but let's put this back to the default settings for the purpose of this tutorial. Another excellent feature for the RBD diagram is the Zoom to Fit option, which will fit the current RBD diagram to the selected diagram window size. Let's, for example, make our diagram window small by sliding the window slit across to the right. Now we cannot see our RBD diagram in full, and to have this diagram full in view fitted to the diagram window, we use this bottom toolbar button labeled Zoom to Fit. Now we can see our RBD diagram reduced in size and fitted to the diagram window. The Zoom to Fit option is very useful when constructing your block diagram, as you may turn out space whilst introducing new items to your diagram. Now that we have looked at all the options on how to control your canvas and diagram page setup, as well as all the features for making your RBD more presentable, let's populate our blocks with some information as well as failure date to obtain the availability and unavailability, which is 1 minus the availability, for our design over the set lifetime of 1 year or 8,760 hours. Let's first edit the first node and rename this to Start. Let's now do the same for our End node and call this Yendi. Before we start to edit our blocks and assigning failure rates, it is very important to first take a look at the system settings to see what the units of failure for our RBD is set to by default. By default, The units of failure for any new RBD system is set to failure per hour FPH. We can change this to be failures per million hours FPMH or failures in thousands of million hours FITS, which is in effect failures per billion hours. Let's leave the default settings and continue to introduce the failure date for our blocks. Let's now edit the first block in our system by double-clicking on it and call this generator. For the description, we can simply enter power generator for our system. Please note that if we had transferred for an existing prediction or FEMKIKA system, all of this information would already be populated, along with the failure rate. So next we would need to assign a failure model for this block and enter our failure rate manually. To do this, we click on the New Model button and see that a new model name is populated with a default setting of a rate model with data entries for failure rate and repair rate. There are a number of failure model types or cumulative distribution functions that we can select from this drop-down list, and each one has its own formula to calculate the probability of failure over the given lifetime. We can look at these various types and their actual formula for the calculation by clicking the question mark button next to the drop-down. As we can see, a new window pops up with the help file section for these types, and when we select each type, we see the corresponding formula for calculating the unavailability and frequency. This helps us in selecting the failure model that best suits our particular block, depending on what data we have available. As we can see, when a different model is selected from the type drop-down, the parameters change to display the required parameters for the selected model. Although any of these failure models and distributions can be used for the blocks, the most common model is the rate model where we need to enter the failure rate. Let's enter a failure rate of 0.0005 failures per hour with a repair rate of 0, which means that this component is not going to be repaired if and when it fails, and see what the chart for unavailability or the probability of failure versus lifetime looks like. As we can see, the probability of this generator failing approaches 1, or very near certainty, after 8,322 hours. Now let's go back and model a reparable component, meaning that if and when this generator fails, an engineer will repair it and get it back up and running. This is where we enter the repair rate in hours for our generator. For example, if we can repair one component per hour, we would enter a repair rate of 1, and if we can repair 2 per hour, the repair rate would be 0.5, and so on. Let's now enter a repair rate value of 1 to model a reparable generator and look at the result on our chart. As we can see, the probability of this component failing now reaches a maximum of 0.0005 after 438 hours, as it can be repaired within the hour. Let's change the name for this failure model to generator and click OK to save the parameters for our generator. Now we can see the block display has been updated with all our data entry, and we can move on to other blocks within our system. Let's model these 3 blocks in parallel to be 3 identical pumps within our system and assign failure models for them. Let's edit the first block by double-clicking on it and call this pump 1 with a description of first pump. Now, we click on the New Model button and call this failure model pump and enter a failure rate of 0.0003 and a repair rate of 0.5, which means that we can repair this pump if and when it fails within half an hour. Let's OK to save our data entry, and as we can see, these changes have taken effect on our block diagram. Let's now edit the second block by double-clicking on it. Let's name this pump 2 with a description of second pump. This time, as pump 2 is identical to pump 1 with the same characteristics, we can choose to select the same model as for pump 1. We do this by simply selecting the name of the failure model from the drop-down list. Once selected, we see the existing parameters are set for this block, and we can OK to save. Let's now do the same for our third block, name pump 3, description third pump, and select the same failure model pump. OK to save, and we can now move on to the final 2 blocks. Let's model these blocks to be 2 identical valves in parallel. Let's edit the first block by double-clicking on it and call this valve 1 with a description of first valve. Now, we click on the New Model button and call this failure model valve and enter a failure rate of 0.00005 and a repair rate of 0.5, which means that we can repair this valve if and when it fails within half an hour. Let's OK to save our data entry, and as we can see, these changes have taken effect on our block diagram. Let's now edit the second block by double-clicking on it. Let's name this valve 2 with a description of second valve. This time, as valve 2 is identical to valve 1 with the same characteristics, we can choose to select the same model as for valve 1. We do this by simply selecting the name of the failure model from the drop-down list. Once selected, we see the existing parameters are set for this block, and we can OK to save. Now we have completed our data entry for all the blocks in our system. We are ready to run the analysis and look at some results. Before we do that, let's look at this very simple case of have one generator in series, with 3 pumps in parallel and 2 valves in parallel. Just by looking at our system arrangements, we can determine the different ways our system could become unavailable. We can deduce that there will be 3 different ways our system could fail. These are 1. Our generator failing. 2. All 3 pumps failing. 3. Both valves failing. These are what we refer to as minimal cut sets for our system, the different number of ways our system could fail, with all of the duplicates removed. So, when we run the analysis, this is the algorithm the analysis uses to determine the unavailability of our system. 1. First, it calculates the unavailability or the probability of failure, as well as the frequency calculation for each of the blocks based on their failure models. 2. Next, it will use Boolean algebra to determine the different number of ways our system could become unavailable. In other words, any block or combination of blocks that could cause our system to become unavailable, and as we learned earlier, we call these the cut sets for our system. 3. Finally, it will aggregate all the results, putting all the cut sets under N or scenario, thereby calculating the overall unavailability and frequency for our system. Let's now run the analysis and look at the results. As we can see, the results are split into 3 different sections. The top section shows all of the system results. The middle section is the importance rankings for each of our block, where the block with highest influence on our system would appear at the top of the list, followed by other blocks in order of importance, and finally, in the bottom section, we see the cut sets for our system, the different combination of component failures that could cause our system failure. As we can see, these cut sets are the same as we expected, with the generator by itself, or all 3 pumps together, or both valves together. The calculation for the unavailability and frequency for each of these cut sets are then used in the calculation of the system results, and we can see the formula for these when we left mouse click on the unavailability of the frequency. Let's now go back to our design and change the criteria for our system to see what difference this would make to our overall results. Let's say that we need not just 1 pump, but at least 2 pumps out of our 3 pumps to be working for our system to be up and running. To model this, we double-click on the exit node for our 3 pumps in parallel and see a value of 1 set by default for the vote, which means that currently only 1 out of 3 is required to be working. Let's change this to 2, which would mean that we need at least 2 pumps out of 3 working. So, now we would expect new results, which once again will be driven by the minimal cut sets produced. We would expect the new cut sets to be a combination of pump 1 and pump 2, or pump 2 and pump 3 and pump 1 and pump 3. Let's run the analysis again and see the new results. We can see now the new cut sets include a combination of pumps 1, 2, and 3, and new calculations for these cut sets, and therefore new calculations for our system unavailability and frequency, along with all other calculations, which are driven by these 2 main calculations. I hope this tutorial on the Item Toolkit RBD module has been useful, and look forward to seeing you in part 2, where we'll look at reports for our block diagram, tabular report formats, as well as diagram reports to a Word document or directly to a printer or PDF writer.